So we are now recording our session and just sharing with you. So I trust you now seeing the lecture slides. Is that correct? Great. So thank you. Today's class is for me it's one of the very interesting topics, and in some sense it will feel like you are seeing you will see things which you're already familiar with, which is fine. I think it has many similarities to the contents of our previous class, which was national material accounts. But we will see how now material flow analysis it still comes from the same concept, which is like a mass balance, but we have a greater level of detail now. And the methods, they come in a different way, let's say, or they follow a different path than the national material accounts, but they are completely interlinked, and we will see how those things interplay. So this is just outline. You'll see that today's lecture will be very straightforward in some sense. So in my opinion, is the smoother lecture so far in terms of density of content and the linearity of the contents. So, sorry, this is wrong. This is we saw it in week 5, not week 6. I will update this. So in week 5, the week before last, we started exploring the balance of materials in a system. And basically we said it could be any system, could be like a city, a region, state, a country, a continent, the world. But our main focus was national economies, right? So for each country, how many materials come in, how much of it goes out, how much is extracted domestically. And we had those several terms that depending on what we consider, what we don't consider, and how we break down things, we analyze that. And we also focused on looking at this global balance of materials in the national economy, how that relates to more socio-economical indicators, especially GDP and Human Development Index. So now we will do, and as I said before, the same type of focus, which is like a material balance in a system, but now we will look at it in a more general way. And more than that, we also now will look at in more detail, also in terms of how the system works, and also in terms of composition and breakdown of these inputs and outputs. So there are type of analysis which are related to this material balance. So people sometimes, and I think we have to be careful with this terminology, because let's say there is some more usual terminologies, which is the terminologies we are adopting in the course, but it's not necessarily standardized. So people may sometimes use the same terms to describe different things. So when we look at material flow related analysis, we have several ways of doing this, and this table tries to summarize that. So what we'll be looking today, it is more what some people call the substance flow analysis, which is trying to do that balance, the detailed balance, and track the flows, inputs, outputs, and internal flows of certain substances. We can also do the same for goods and composite materials, right? So which would be like a goods balance, which we can still use basically the same framework as we will see today for a goods balance. And then when we look at global scale flows of big classes of materials, then it's more related to economy-wide material flow analysis, which we saw in the last class, and also that idea of material input per unit service. So if you remember that, we look at the more broad aggregated categories like biomass, fossil fuels, minerals, and things like that. So here we can see one of the core distinctions between these two focuses of the material balance, where what we saw before was global scale, not global, but like large scale, aggregated, economy-wide. And what we will see today is like in detail, process specific, and in most of the cases, substance specific as well. This is where this becomes more useful. So also we see that economists, they do this same type of balance, but looking at economical exchanges, which is normally characterized by money. All right, so money value flows across economies, across sectors of the economy, and so forth. And we saw that most of the national material accounting that we do is based on the economical flows. So one of the methodologies, and possibly the one which is more, how to say, but well, possibly the one which is which has the best capability of tracking the whole system is the input-output based methodology to determine the material flow we saw before. And that methodology relies heavily on economical exchanges. So basically, they try to translate money exchanges in terms of aggregated material exchanges associated with that. But us as environmental engineers and other engineers interested in the environmental area, the money flows may be a tool for us to understand what we actually we are concerned about, which is the flows of materials and energy, or the exchanges of material and energy between the environment, the society, the economy, and the sectors of the economy. So that's where it's not necessarily, sometimes it is a direct measurement of environmental impact, but sometimes the indirect indicator of pressures on the environment. And that's why we're interested in that. So for economy, they use, they model out how, or they try to understand how things work and then model it to make predictions and take actions. Well, as we normally know, these are not perfect, and very rarely you see economical projections being fulfilled completely. So economy is quite unpredictable. Who could predict? Oh, well, they predicted the probability of coronavirus happening. So if you look at reports, even from the year before, I think from 2019 or 2018, people were talking about the high probability of having a pandemic in the next decade. But it's hard to say what this pandemic will be like, when it will happen, where it will happen, how it will spread. Now we know more. Maybe now, based on this experience, we can have better ways of preparing for it. But what I wanted to say is like, even something which is so well monitored and so well studied as economy is super hard to make predictions, okay? Because mostly because there are natural and human factors which we do not have enough information to map, let alone to predict. And then the material balance for the regions or institutions or any closed system that we define as our system, it leads to the concept of material flow analysis. And I come back here with that equation that I showed in the first in our first lecture when I was trying to introduce myself and areas of study. And as I said before, so this is a very general equation which maps exchanges within a defined control volume. So tries to balance the rate of change of things in the system with the exchanges across the boundaries of the system. So this is the same principle that we apply for all type of balances of conservative things. As long as things conserve, we can do a balance if we have enough information to map all the pathways. So why we want to do that? So that's a bit repetitive. We already discussed quite a lot in terms of when we looked at both environmental ecological footprint and when we looked at the national economy-wide material accounts. So looking at the extraction and looking at the extraction of materials from the environment give us indications of environmental pressures over the resources, and especially for non-renewable resources, we want to see how quickly we are depleting them, and if we will have shortages in certain time frame. And for the renewable resources, it's also important for us to understand those flows, because we want to understand if we are extracting these renewable resources in a rate that they can be naturally sustainably replaced. Otherwise, you are also depleting them anyway. Now, when we look, as I said, the focus of our analysis now is more detailed, especially in a substance level. Why is that? Well, because then we can track more in detail, let's say mining. We can look at the, not say sustainability, but we can look at the pressures of extractions and consumption over a certain given mineral of value or a certain given element, such as cadmium or zinc or gold or titanium, I don't know, or any of these minerals which are of high value, or elements which are of high value. And then also we will try to understand our impact in terms of, because at the same time we are looking at extracting things from the environment, but we are also looking at moving things from their original environment to a different environment, be it our own society, and we will call it, we call it anthroposphere, so our all human inhabited and human controlled environment. And sometimes moving things from nature to our environment is not a good idea, because these things can be toxic for us. So an example would be mercury, right? So mercury naturally occurs in some minerals and soils and even waters. But if you extract mercury-rich minerals and you refine mercury and you put it around, you're increasing the risk of contamination and health effects on us. Same thing, lead. So if we extract the lead from nature, we refine it, we put it in gasoline, as people do, and then we burn that gasoline and we put that lead in the particles that go to the air, also big trouble for us, right? Same when we put lead in pipelines or put lead in paintings. So when understanding this flow, when we look at in detail in terms of given substances, it's even more important for us to map internal flows in our society and in our territories and economy, because these internal flows can be linked to certain health effects or environmental effects. So what I hope to convey here is like looking at the extraction side, it has importance in terms of environmental resources and environmental pressures. Looking at the internal flows in the society or in the anthroposphere, it is important because some of these flows inside our society, uh, it they are related to impacts to us, and also understanding these, we will understand which are the sectors which are more responsible for certain consumptions, and for where are the demands and what's the dynamic involved in those demands. And finally, uh, we also are interested in the output of specific substances, because these outputs also can cause impact, correct? So as I was saying, mercury and lead and some substances like these, when we throw them in the environment, when they leave, suppose our system of control is like an industrial process, but when they leave the industrial process, we want to map how much is leaving where and in which form, because that may be related to direct and indirect environmental impacts. Also, that will help us understand the magnitude of the anthropogenic, the flows created by the humans compared with natural flows. So this is a case, I don't know if some of you remember that, there was a volcano eruption in Iceland in 2010, and it expelled a massive cloud of particles in the atmosphere, and this cloud then dispersed over Europe. And there was, besides, the normal side effects of particles and like respiratory problems and things like that, there was massive cancellation of flights because it was so heavy, and the visibility was so impacted that flights in many airports throughout Europe could not happen for several days. So it's also important for us to understand that there are what we call geogenic flows, flows which come from the nature, not necessarily directly from human activity. And understanding the magnitude of those flows compared with the magnitude of the flows coming from the human activity is also important, because that will help us prioritize action. So, and that will help us understand, what is caused by humans and what is not caused by humans. Classical example again, climate change. So people may come with these ideas of like, no, methane emissions come from natural mangroves and swamps, and these methane emissions are much important than the methane emissions that come from human activity, for example. So being able to map how much methane we emit from wastewater treatment, we emit from natural gas extraction and transport and other activities, and comparing that with the natural emissions could give us an idea of how much we can influence in terms of change. So these are just some examples. Uh, Here is let's say it's not a case study for us, but just some news about a disease that was detected in Japan in the 1960s. And until today, people are impacted by environmental impacts that happened back then in the 40s and the 50s. So I will ask you to access this website quickly and have it's not a large text, so I will give you maybe 3 minutes if you can just quickly read through this. I'm just copying the link here on our chat. If you can quickly have a look on this news, we will have a small discussion about that, and that will help us exemplify the importance of understanding these flows of materials and mapping and controlling them. Okay, so I will give you here 3 minutes, and later we'll come back for discussion. So these are the questions we would like to discuss. Okay, please have a look at that text. And I will just turn off my camera to not distract you. Also because it's awkward to be quiet looking at the camera. Okay, so back to action here. Let us discuss these questions, and I also have another question for you. So this is just to look at different ways we can respond to the detection of an environmental impact. So anticipatory means when you feel that thing, or when you perceive, when you have evidence that things can happen, you act beforehand. Whereas reactionary is like, oh, after things happen and then we start seeing the consequences, then you go and try to correct it. So very easy question. What did they do in Minamata? It was clear reactionary. Thank you. Yeah, it was clear reactionary, as our colleague pointed out. It is like they detected there was a disease. Later, they confirmed that disease was linked to discharges of mercury coming from the industrial process, and they still didn't do anything. So later, when things got much worse, then they acted, and later on, even years later, they end up cleaning the environment. But when that happened, it cost a lot to start with, and worse than that, so many people had been affected, and because it's a cumulative effect, and it's like a, it's a permanent damage to these people's health, they still have the consequences today. So, well, we don't even have to ask what's a better method. It's clear that if you can proactively anticipate that problems will happen, or you will act when you start detecting the problems and avoid it to become worse, it will cost less and will cause less impact. And do you have any feeling what can be? Oh, we talked about Minamata, which was a problem with mercury coming from a chemical plant, but uh, if we think about all the things that there are many other examples of similar things that already happen, such as the PCBs, which were widely used everywhere, and later we discovered that they are bioaccumulative and cause problems especially in children. We have, localized problems with lead. We had now recently all the problems about related to flame retardants, the PFAS, and they're still under investigation, and there is a lot of research done, including in our school, regarding these substances. But do you know any other cases where you think could happen like this? Does anyone have any idea besides these ones that I cited? Chlorinated compounds. Yes, that's one. Correct. So lead-based ammunition. That's true. Yes, there is a lot of before the ammunition was all about uh, it was made of lead. In- Yeah, I like my original language is Portuguese. So in Brazilian Portuguese, one of the one of the ways to say fire at someone is like to throw lead at them. Just how widespreadly the lead was used. Yes, correct. And yeah, and true. And they, if they are getting rid of that, but you know, w- possibly the military will be disposing that correctly, we hope. But what about lead ammunition in the hands of maybe less equipped military, or in the hands of civilians? In some countries where civilians can have guns, and or in the hands of uh, informal military groups like terrorist groups and things like that. If they have stocks of that and this is not properly contained, this can become a local serious case of environmental contamination. Same with the chlorinated compounds. There is a general movement of reducing, especially extremely toxic chlorinated compounds, which used to be widespreadly used as pesticides and similar things. But still, hard to say if we have track of all of it that's out there. So there might be some non-detected storage or non-detected usages in the past, which can still be causing damage, or can become start contaminating as the containment structures fail. True. I was also looking at news this weekend about radioactive water coming from the Fukushima accident in Japan. So that's also becoming a big deal because they're having to pass because they have to keep the failed reactors still cooling. So they have to continually pass water in contact with the reactors, because in a normal nuclear plant, the water doesn't get in contact with the reactors. That is an indirect heat exchange. But now, because the things are broken, so there is contact of radioactive material with the water, and now they have to store all that amount of water, and that can not maintain it properly. Accidents can happen anytime in the future. Okay, so let's keep this Minamata example in mind, because at the end of our lecture today, we will come back to this and discuss how we could have used the techniques we'll be discussing to help with this problem. Thank you guys for your contributions. Whoops. So just introductory, like more formal concepts in terms of these material flow analysis. So first of all, what is formally material flow analysis? So by the definition of these authors, material flow analysis is a systematic assessment of the flows and stocks of materials in a system defined in space and time. In other words, it's a detailed systematic mass balance for a given system that we define. This book is available through the library, so you can even access the electronic version via this link. So it's good to check it out. And if you decide to, if you're going to do work on that, then I recommend you to look at this in more detail to support your activities in this. So if in your work life you are tasked to do a material flow analysis, this is a very good way to start and be more support your work on that. So an interesting story here, which I find very nice, is of this Italian. Well, he was a physician, but definitely he was a great scientist for the time. His name is Santorio Santorio, and being a physician but having a very scientific mind and also possibly being influenced by friends such as Galileo Galilei, he did several types of experimentations, and one of them was a mass balance for himself. So for 30 years, he weighted himself, and everything he ate, everything he drank, and his urine and feces. So he was trying to do the mass balance for his body. And when he compared the weight of what he had eaten to the waste products and his weight changes, he detected an imbalance. So he would eat much more, he eat and drink much more than he was excreting in terms of urine and feces. And very smartly, he concluded that the difference could be attributed to respiration. So at the time, he kind of said we respirate by the skin and by the breathing, and he said most of it will be coming out through the skin. Later on, this was changed, but anyway, like it was very nice that he could. First, very nice that he did this experiment. Secondly, that he could uh, figure out that respiration was responsible for closing the balance. But more important than that, the idea that things would conserve, that mass will conserve, so the balance must close, is a very central idea in what he did. And this feeling that things must conserve is even much more ancient than Santoro. So in the ancient Greek times, one of the main questions that the philosophy had was like in terms of hydrological cycle. So they were puzzled by the idea that, well, you see rivers flowing, the water is continuously coming from upstream to downstream, and they asked themselves where this water comes from. The other thing is the rivers flow to the ocean, but the ocean levels are more or less the same. So they're like, well, now that we are putting all this water in the ocean, where is this water is going to that the oceans don't overflow? And that led to several interesting theories. So it was not straightforward that people figured out the closed hydrological cycle as we know it today. But it's interesting to see that intuitively we have this feeling of conservation of mass, that, you know, things, they may change, but the total mass of things remain the same in the system. And that has been first formally put forward by Lavoisier, who possibly we've seen this before, that in a chemical reaction, matter is not created, not destroyed. It changes and is transported, but the total mass, total mass as a measure of the amount of matter there will remain constant. So this is the conservation principle, and this is ultimately which leads to that more generalized equation that I like showing. And this is the principle behind basically everything we do in environmental engineering. So in a general terms, for any closed system, and here we are looking at the whole anthroposphere, and anthroposphere means this environment which is dominated by human activity. So basically human activity influences the whole planet, and if you want to put it even beyond the boundaries of our planet, because we are now, you know, sending uh, probes to asteroids and taking things from there, and landing on Mars, landing on the moon, sending probes uh, to other planets. So human activity influences a lot, but we can determine this environment which is completely dominated by the human activity, and that's called the anthroposphere. So since we can do the balance for any system, we can do a material balance for the anthroposphere. So the way things happen now, we have now our natural environment, and the anthroposphere is inserted in that natural environment. And we are interested to look at these exchanges, as we've seen before, of things which we extract from the environment, and looking what we do with it, including what we keep inside and how these things flow inside our anthroposphere, and what we then emit or we discharge in the environment again. And these discharges, they can be in terms of air emissions, emissions to the atmosphere, emissions to the water, which here we are calling sewage, but we could call it wastewater more uh, directly. And we also have some diffused emissions to the water through contaminated rainfall and percolation in the groundwater, and solid wastes as well. So solid materials which we put out there in the environment. And interesting to say that my research area is in fact looking how emissions that come from wastewaters and from solid wastes go to the atmosphere. So trying to understand how these two components here influence this component here. So I can say that I work at this end of the balance more in terms of research work. So just to formalize some of these terms that we've been using. So the environment, we can divide it, and this brings me back when I was doing my primary school when first I heard of these terms. And at that time, we didn't have anthroposphere. I didn't learn that when I studied. So we just learned about the environment where we have the hydrosphere, which is the water bodies, atmosphere, then biosphere, which is just the living organisms, and the lithosphere, or pedosphere and lithosphere, which is like this is soil and this is the crust of the earth. But then it makes sense for us to talk about the anthroposphere, which is, as I said, that environment completely dominated by the human activities. And most of it is built environment, right? It's where we create a new environment which is not natural. So when we are doing a material flow analysis, I said we can do it for substances or goods. So when we talk about substance, it is a element or a compound which has uniform function or constitutional units. So I will not expand here on the chemistry aspects of it, but just to remember, elements are just those that are characterized by like one atom. Not they are made of one atom, but they're like elements is the collection of all the atoms which have the same chemical atomic composition. So like gold is just like one type of atom which makes gold, and nitrogen and oxygen. And then these elements, they sometimes can combine in compounds. So CO2, the molecule of CO2 is a combination of one atom of carbon, two atoms of oxygen, two double bonds between carbon and oxygen, and then this makes a compound. So either a element in itself or a compound makes what we call a substance. So it has a unique individual chemical composition. Whereas a good is a mixture of several substances which makes something which normally have some economic value and which could be positive or negative. And here we say some goods have no economic value, but depends on how you define economic value. So maybe they don't have direct economic value, but they are still linked to the economy, because maybe rain doesn't have economic value. You don't sell rain, you don't buy rain, but the lack of rain can impact you, or the excess of rain can also impact the economy, right? So even if they don't have a value aggregated to them clearly, they are important. They have economical and environmental impact. So is it clear the distinction between substance and goods? Like say a pen is made of several substances. One of the substances could be the polymers that made the plastic, and there might be more than one type of polymer here. Possibly we have, forgot the name of the element here. Not sure if it's vanadium, thorium, no, I can't remember. There is one very rare element that people use to make these pen tips, which was like one element, one substance, but we make a good because we combine it with other things and make a pen. Okay, so we can do the balance for materials. So when we talk about materials, it can be either a substance or a good. So when we do a material flow analysis or material balance, we can look at it substance by substance. And the reason why, whoops, I'm anticipating things here. The reason why we want to look at substances is sometimes because that substance is exactly where the environmental impact is associated, as we talked about mercury and lead. So they are substances. So the goods containing them are also of environmental importance in that analysis because they can lead to the release of that substance. Or we can look at goods in themselves uh, more now in a more aggregated way. So this can be either raw materials or modified materials, all right? So we can use that just as a general thing because if we know we are doing the analysis for a substance, we can call it a substance flow analysis. If we know we're doing the analysis for a good, we can call it a good flow analysis or a goods balance. But if we don't know if we're talking about the general practice, because it pretty much follows the same framework, then we call it material flow analysis. That's why we call it material flow analysis. So just an exercise here, we're looking at copper. So copper as the collection of all the atoms which have 29 protons in their nucleus is an element, which is a substance. When we look at it in the mineral that contains copper, so this is already a good because it's a combination of several substances which have a economical value. And then, if we look at the objects made of copper, the objects themselves will still be goods, even if it's pure copper. But this is like copper formulated and built in a way that it has its use and value. So it's something made of copper. But then why we are interested in goods? Even if we are doing a substance analysis for copper, tracking where we possibly will have much more data to track the goods than the substance itself. So sometimes we first will have to do a goods balance and then convert that in terms of this composition of that substance in those goods. And all of them are materials. Another important point here is process, because we'll be talking about process all the time. So, yes. A pure copper bar will be a substance or a good. Well, the substance is copper, so the copper contained in that bar is a substance. But if that bar is there for some reason, so that bar in itself as the object is a good. Does that make sense? So if you look at, if you're doing like how many bars of copper were sold from industry A to industry B, you're doing a goods analysis because you're looking at that object being transported and sold. But then if you look, oh, how much copper was contained there and flow between these two industries, then you're doing a substance analysis. In a more complex thing would be like, well, how many lithium batteries were produced by certain country? You have this many batteries, so this is a goods analysis. Or how many tons of lithium batteries, yes. But if you look at how much of lithium was used to produce those batteries and how much was transported to another country, that would be a substance analysis, right? Now processes. So processes are, by definition, the transformation, transport, or the storage of goods and substances. So in gross terms, processes anything you do with goods or substances. So the process of doing it is called process. And the examples are waste separation, incineration, release to the atmosphere, hydrosphere. So the way we look at processes, we can look at processes in several degrees of detail. So we can do like what we call a black box, which is just we have the whole process and we look at inputs, outputs, or we can break it down in sub-processes. So we can then choose smaller units of that process and then map how things flow inside. So basically, as you can see, these flows here, 1, 2, 3, 4, and 5, they are flows in and out the system. But then we have flows within the system between the sub-processes. So we can do a material flow analysis, consider these two levels of detail, but the typical thing is for a material flow analysis is to break it down as much as we can. We disintegrate a process in sub-processes with as much detail as we can, and be mindful that each of these sub-processes probably can be broken down into the smallest sub-processes. So there is a level of detail in which you can do that, and that level of detail mostly is determined by how much information we have about it. it wouldn't make sense to break it down and not being able to map the flows. Then why we are breaking it down? Then well, it still may be value in terms of understanding how things work and say, well, we need more data for understanding these sub processes and these flows. But then possibly our analysis will have to go one level up and aggregate then to the level where we have information about the inputs and outputs for that process. And also the thing, another concept here is stock. So stock we are familiar with because we looked at it before in national material accounts, and it's just the amount of material stored in the process for a period of time. So that's the stock. And normally in our balance, we look at changes in the stock because we say that the input is equals the output plus the change in the stock. So if we have a positive change in stock, or if we accumulate materials within that time period, then we'll have an output which is less than the input. On the other hand, if we decrease the stock, it means we have more output because we have all the input plus the change in stock as the output. So here we have one quick activity just for us to practice that. Here we have a periodic table of elements. I also have a periodic table of elements in my desk, which was a Father's Day gift that it gave me. So we have a periodic table of elements. Can you please choose one substance, which could be one of these elements or a chemical compound formed by combinations of these elements. So choose that one substance, think of one good related to that substance, and one process which affects that good. Can I have some examples here? If you can put like substance this, good this, process this. Can we list some? I think that activity will be good for us to right. So our friend said NaCl, so sodium chloride, which is the substance, which is salt. And do you think, and you're also listing salt as the good itself, correct? And which process involves salt? Which is one of the processes that salt can be affected by? While you post that the process, another friend said lithium as the substance. Can you think of a good that contains lithium? Someone else can think about it. So friend said, yes, we have lithium ion batteries, which is a good. And you already list the process. The process of making them is already a process that affects that good, for sure. I'm still waiting for some example that can come from the same colleague or someone else about a process that affects salt. We all know it. If you put salt in your food, yes, hydraulic mining, correct. This is the process of making salt. If you mine salt from water. I was also going to say cooking. If you have salt, you put it in your food, this salt will be changed by that process. So it will be dissolved and will be mixed with the food and we will eat it. So another friend here listed the pure copper or nickel. And the good is the nickel silver bombilla for mate and for melting. And the process is arc melting, annealing, hot working. Correct. Yes, that's a clear map of substance, good, and process. Thanks people for the engagement. So I think with that, it's good for us to think about it because it helps us clarify and properly use these concepts. All right, great job. So one of the main points in doing possibly the initial step of doing any balance analysis, and that serves for even like hydrological balance or national, not national accounts, no, but yeah, material flow accounting, economy-wide flow accounting, and all of these things is to define the system. So which are the boundaries in space and time for which we will be doing the analysis? All right. So this system can be the anthroposphere, can be the whole planet Earth, as we said, can be a solar system, can be a natural economy. And when we are talking about material flow analysis is quite useful to look at smaller and more detailed systems, such as an organization or a company or even one industrial process in itself inside an organization. So, and the reason why it's useful for that, because sometimes if we have a smaller system, we possibly can give more data and have more complete description of the balance for that. But it can also be applied for a whole country, and we will see examples of that later. So what is a system? A system is defined by a group of components and the connection interaction between them, which serves a certain purpose. So the components of a system are either processes or flows. As we see processes, these processes are linked by flow of substances between them. And as I said, a system can be a lot of things with different spatial and temporal scales. And the system boundary is just like which are the limits of the system. So anything within those boundaries will be accounted as internal, either internal flows or internal stocks. And whatever crosses that boundary will be inputs or outputs. So when we look at any given time, flows coming in a system we call imports or inflows or inputs, and flows leaving a system are export or outflows or outputs. This we are all familiar with. So what's the structure of a material flow analysis? So we will have a system characterized like this. So we will have several processes inside the system. So we'll define the system boundary, and then we look at all the processes and flows that happens inside this boundary. And then we will have the inflows and the outflows. And possibly we will want to know where these inflows and these outflows are coming from and going to respectively. So even if we are not breaking down these processes and looking at these systems separately, but mapping where it's coming from and where it's going to is extremely useful, right? So again, suppose we are talking about mercury and we're saying, well, we have this company which outputs this much mercury. Knowing how much mercury is output is already important, but knowing where it goes to, it's also important. So is it output as a manufactured good, like as a mercury thermometer? This is one thing. But then, or it's output as an emission to the water, or emission to the soil, or an emission to the air. So that will have a different implication for us. So mapping the form and the destination of these inputs and outputs is important. So yeah, here we have an example of cadmium flows in the, so this would be in a generalized environment. We have here lithosphere, atmosphere, the ocean representing hydrosphere, and the anthroposphere here, like the humans. And here we have a balance going. We have like stocks. So these are how much is stocked in each of them. And here we have the flows going out, or depending on which is your system. If your system is atmosphere, you have flows coming in and out. If your system is the ocean, then it will change which flows are coming in and out, and same for the humans. And looking at these, what is your assessment in terms of the anthropogenic flows compared to the geogenic flows? So the anthropogenic flows will be these ones coming to and going and coming to and coming from the humans. How does that compare with the natural flows that we look here? Are they same order of magnitude, the larger? So what's your feeling? So our friend here is questioning why we actually want to compare with geogenic flows if normally the human-driven flows, as we see in the figure, are much larger. Well, yes, you are right. Most of the cases we will find that humans drive flows much larger than the ones in the environment, but that's not always the case. And especially if we go to smaller systems, such as like one industrial process or one small community or a city. So in those cases, sometimes we will have geogenic flows which are larger, right? So, and then to be able to say it is larger or not, it is uh, it is important for us to drive that. So let's give some examples. Uh, well, there is a locality here in Sydney that they have a wastewater treatment plant, and the people complaining about the odors produced by that wastewater treatment plant. But that wastewater treatment plant is close to a mangrove. So the people come and say, well, these odors that I'm smelling come from that plant. So that plant should change their operation to avoid this impact on our community. But then the plant can argue, no, most of the odors don't come from us. It comes from the mangrove behind. So in a situation like that, we would have to have accurate ways of determining how much of the odor substances are coming from each of these, the geogenic flow coming from the mangrove, the anthropogenic flow coming from the plant, to have an idea how much potential impact they will cause. This is one example. And another example would be sometimes with arsenic. Luckily for us, very rarely we have arsenic occurring in the environment. But sometimes some environments have high levels of arsenic, so you may detect high levels of arsenic coming from in the water itself, and this may come from the dissolving of minerals containing arsenic. But then you can have this is a real case that happened in Brazil a few years ago. Then you have a mining accident, and there was uh, a lot of mining slurry and wastewater came to a river. And then came that then people detected arsenic was there is arsenic in this river, and then they said well, it was the mining accident. And the mining company was no, the arsenic is naturally occurring by the dissolution of the minerals. So that again is a situation where it's not clear where it comes from, and it's not clear which one is more significant. And we would have to do a we would we desire that would have the capacity to accurately model how much came from which, so we can decide in that case liability, but it can also decide actions to be taken. Does that give some valid examples for your question? Cool. And here we're looking at a cadmium cycle in the Swiss economy as an example. And what do you see here? What this analysis tells us? To start with, true, anthropogenic flows in the system are much larger than geogenic flows in the system, but geogenic flows are not uh, negligible to start with. The second problem is that they come through, like they come as atmosphere, so that's another problem because then people possibly will be more exposed than maybe if it came in the lithosphere. But what else this balance tell you? Are these flows balanced? Well, we can say not really. We have a input of or an inflow of 111 and an outflow to the environment of 6. So good for the external environment in that country. Like look that this is the whole boundary of the country. So there are flows to the internal environment of the country, but not to the external environment. So good for the neighbors, which are not receiving too much cadmium. But we see that suppose this is an yearly balance, there is a lot of cadmium being stored, as our colleague just pointed out here. A lot of cadmium being stored in that country. So it's a huge liability. If it is being stored in the environment, it's a huge problem. And we can see here some significant flows, especially to the uh, pedosphere and lithosphere. But also very concerning, a lot of stock in the anthroposphere. So it means that we are surrounding, or these people are surrounding themselves with cadmium. And if it's not properly contained and depending on which form it is exposed, it can be several health damage. There is a question here. So, oh, good point. So our friend says, if we are looking at some system and there is an imbalance, it means that the outputs or inputs are not being tracked or the materials are staying inside the system. That's a good question. We would talk about that later, but that's a good point. Like, if you do a material flow analysis and you find an imbalance, what does that mean? Does that, well, in principle, yes, if your balance was, if you could track all the flows and you find an imbalance, it means it's being stored in the system. But it may be as well that your data about flows are inaccurate. So either you are missing a flow or you are quantifying it wrongly, some of the flows. So that there is no standard answer for that. So in imbalance, we always raise questions, but then yeah, you have then to evaluate how confident you are that you've been able to map all the flows and that the quantitative data is accurate. So and more formally, you can do uncertainty analysis on that. So as long as you think you've mapped all the flows, you've not missing any pathway, you can then do an uncertainty analysis to see how sure you are of what is the confidence interval of the changes in the stock or in of each flow. There are statistical frameworks to do that. Cool, good point. So this is just I will not dwell much here because we have to progress with understanding more the method, but this is just like where cadmium can come from, and we can see there are intentional uses where we use it because we want the value that cadmium adds uh, to these goods. So for example, it can be used as a pigment for some plastic and in batteries, of course. And there are unintentional uses. So sometimes there are flows that we don't want cadmium there, but it came before because it was there as a contaminant in fertilizers and other materials. And again, if we have accurate data, we can actually look at where it's coming from and where it's going to. And that's very useful as a planning tool and an assessment tool. So just a few more terms. So physically speaking, flow or mass flow rate is just the amount of mass per unit time that goes through some conductor. And the flux is the flow per cross section. So then it's like, in some cases, we can first quantify the flow per cross section, then we have the total output. Again, back to the type of work that I do, a lot of my research is about trying to quantify the fluxes, the exchange of material substances between water and air. And all the models we have for that, they are in terms of a flux. It's just amount of substance per second per meter square. After we know that, then we multiply by the area of that boundary, and then we have the total flow in terms of mass per unit time. So these are several uses that we have for material flow analysis. We can monitor the accumulation, depletion of stocks and pollution levels. We can then use that to help manage the resources, help them manage the impacts to the environment. And then also it can serve to integrate scientific data. So what you probably will find is that people might be doing detailed research as I just mentioned, in one component of all that balance. So then we can use a material flow analysis to integrate all those outcomes in a complete balance for that substance, for those type of systems. And then that can also be used as a decision-making tool and also a guiding tool to help us improve systems, processes, and goods. So we can then look at different processes or different ways of doing something and map the flows and see which ones are more beneficial. Questions so far? So let's quickly look at the method of doing this. So this is a general schematics of the steps of the framework to conduct that. You probably saw something similar to this before. So it's somewhat similar to the process of life cycle assessment to some extent. And not sure if any of you did the hazardous Jesus Christ, hazardous waste management course with me last term. But we also look at a auditing for hazardous wastes, and we basically the auditing for hazardous wastes is a material flow like this, material flow analysis like this. So an important point here is problem definition. And that's something that we sometimes neglect. I was just talking to a friend this weekend who's also he's a lecturer in AGSM, the Graduate School of Management, and he was talking about how important is the problem definition, which most people neglect. So he was basically saying, yes, it's hard for people to realize how important characterizing the problem before we try to address the problem is important. So what exactly we're trying to look at? Later, when we know what we are searching, then that will guide our decision in defining the system. So which will be the size, the boundary, and the processes that we will include in our system. So after the system is determined, we can then go to the mapping of flows and stocks, which is, let's say, the flow analysis per se. And that, again, we will have different steps that, because possibly we will look at the flows to start, like which flows are there, where things go to and come from. And most of the times we will have the first-hand information that we will have will be in terms of goods. Especially for industrial processes, most of the information will not be substance specific, will be good specific. This company buys this much of wood to produce this much of paper. This much of paper will be sold to these and these and these and these other companies. So we will be more about goods, but then we can determine the concentration of that substance in each of those goods, and then we do some simple chemical calculation to balance the substances themselves. And to that, we will add then the emissions and the fugitive, like the unintentional flows of that substance. We have here a question. Can you take the Minamata as an example to explain the procedures? Yes. Okay, I was going to ask you guys to do that, but I can do that then. Yeah, all right. That was after we looked at the method, I was going to ask if we can do the Minamata, how we could have applied this in Minamata. Yes. So I'll just finish this and then we go to that example. Cool. Finally, after we have the output of that, we also want to do a good illustration and interpretation. So being able to, because as you can imagine, depending on the complexity of your system, mapping this may be a big job. And then summarizing that information in a way which brings the clear messages is not always straightforward. So it will be very hard to look at a big table or a big, a big Excel spreadsheet or a big uh, whatever programming language you use, a big R or MATLAB or Python output, and interpreting that as a practical outcomes, not always straightforward, especially for non-technical people or not, people who are not familiar with that. So being able to then summarize that information in pictures or summary tables or diagrams, which then can give us a complete picture of the balance, is very important. And then interpreting that and making decisions based on that is another important So let's just show some examples with simplified systems before we jump to Minamata. That's fine? So this is a simple balance where we have one system here, and this system contains one process with one inflow and two outflows, right? So this here is the mass of this inflow and this outflow. So this is mass of goods. So suppose this is like plastic and this is two things made of plastic. So this is a goods balance to start with. But then we look at this goods balance, and then we have in each of these flows, we characterize the chemical composition for two substances, the green substance and the red substance. So the number of squares here, it's proportional to the concentration of that substance. And here we see that our input has a mix of these two substances, but then the outflows, one of them contain all of the red substance and a little bit of the green, and the other one contain majority of the green. So if we're going to do a balance for these substances, we will have then to multiply this goods mass flow by the concentration of that substance in the goods, right? So this would be a substance flow analysis for each of those substances that we looked at, correct? So this is just an example. So we just looked, oh, sorry, we just looked at our, here we have 10 red square, 15, so that's 15? Yeah, 15 green squares out of 60, and then we multiply that based on the concentration in each. So then we have a total mass of that substance coming in each of these flows. So that's the initial illustration of how we first do a goods balance and convert it in a substance balance. Both of them will be a materials flow analysis, okay? So one will be a material flow analysis for the good, one will be material flow analysis for each of these substances. And this is what the result will look like. So we have a boundary again, here we have more than one process, and we now have internal flows. So we have mass flows of the good or substances, and we have mass flows associated with imports and exports, and we also have internal flows between the processes. We have the direction of the flow, that is important. So we see that flow A comes from process 1 to process 2, but flow B then returns to process 1, from 2 to 1. And here we have the stock. So the standardized way we report the stock is like as two numbers. The first number is the amount of stock accumulated at the beginning of the time frame of the analysis. And then here we have a plus or could be a minus depending on the way it changed. And here we characterize the change in stock within that time step. So we normally don't put it together. We have the breakdown between initial stock and change within the time frame. And then hopefully it will be balanced. So and please mind that the balance is not between the stock itself, it's between the change in stock. So here we see that the total import is equals to total export plus the change in stock. Okay? And then we, as our colleague pointed out before, we want to see that conservation of mass. If we don't see that conservation of mass, it is either that we forgot some flow. So what we can have here is like, as we say, the sum of inputs equals sum of output plus change in stock. And then we have a evolution of stock in time. So we say that stock at the end of a time period is equals to the stock at the beginning of the time period plus the change in stock within that time period. So this is for this balance here is in that time period, and this is the evolution of stock. And then with that, we can map the evolution of stock through time. And as we see, is if this balance is not, it doesn't close the balance, we have to understand why it doesn't close the balance. And it can be for several reasons. One of them is the inaccuracy. So we may have either inaccuracy in the goods balance or in the substance characterization, and that leads to uncertainty in the values, either the values of flows and or changes in stock. Another reason is that we may have completely missed one flow. So we may have forgotten a certain pathway. So we may have forgotten some diffused emission, or we may have forgotten some hidden flow. Hidden flows not in the same sense we used the hidden flows before, but maybe uh, we're not clear that that substance is present in some other good that's being exported or imported. Or we may also have missed stock. Maybe we do not characterize all the stock in that system. As I said, the bigger the system gets, the more difficult it will be to map all the flows and all the stocks. So possibly we will have more ability to map it. Whoops. Hello. Did it freeze? Did you guys hear me? Okay, thanks. Because for me it appeared completely frozen, and I could not even click in the screen, so I was afraid I lost connection. So yeah, as I said, most likely in smaller systems we will have more better information or more ability to track all of this. So here is just an activity of conservation of mass. So if we look at this, can you figure out how much is the output number 2? Supposing that all of this is accurate. So how much we have of, right, cool. Let's see. Well done, people. Yes, so we have here one input 4, 3, so together we have 7 as input. We have one output with 5.5, another change in stock with 0.5. How much we need to balance this is 1 kilogram per hour. Good. So basically the analysis can do that in a complex diagram. So friend asks, does it also depend on the goal of the study as to what flows are mapped, or are there more specific standards like for LCA? There are no like standards for that, but because you want to do a balance, so you want to map all the flows which contain that substance, right? Otherwise, it's hard for you to close your balance. And then if you don't close your balance, it's hard for you to identify any failures in doing the balance. Okay, so maybe suppose you're saying, oh, I'm just interested in atmospheric emissions, so I will not map the wastewater and the solid waste. But then with that, it's hard for you to check, well, my determination of these emissions are accurate. Because if we will naturally imbalance this because we are neglecting some flows, then it's hard for us to okay. Hard to say. Yeah, so you're saying, oh, if we don't have a standard, how will you make sure this is done in good faith and everything's captured? It's expert judgment, right? So that highlights the importance of having expert people in environmental agencies and also in like you know NGOs and society independent society organizations, because if you do not have experts to check things like that, the supposed experts doing the analysis can do whatever they want, right? So yeah, no, there is no standard for this as far as I know. And I find it super hard to have a standard for this because yeah, as you can see, it's so process specific. And depending on if you look at goods or substances and other things. So I think we will have to rely on the people receiving that information, they having enough capacity to judge. And of course, it must then be very well reported to give the people the capacity to judge what has been done. What I can tell you is that scientifically speaking, there is, depending on the flows we are talking about, there is a lot of uncertainty. Correct. LCA is also subject to the same inaccuracies. Maybe what, yeah, maybe LCA, the inaccuracy or the capacity to hide data is the same for both, but maybe LCA is more like a, yeah, exactly. So you have, because it's something that everybody does the same way, so if everybody does it the same way, so people are more familiar with the process. So it's more likely you find people who already will be able to judge it straightforward. Yes. But what I can tell you is, like, scientifically speaking, our ability to map certain fluxes, certain flows, it's still limited, including the things that I do. The things that I work is exactly to look at the limits we have in quantifying those water atmosphere exchanges. And we are working towards making it better, but it's a long way. And it's very process specific as well. There is a software to do that. Oh, there are several softwares to do this, but this one is cool because it's free. So you can go there and make an account and then start playing with that. And it has several capabilities here. You can make a model graphically and then input the data that you have, and then you can calculate the remaining data if you have enough data to close the balance. And it's cool because it also does some uncertainty analysis together. So the interface will look like this, and you will have, like, you can build the system, build the flows, and then put the information that you have and calculate the ones that you don't have. So now that we go to examples, we can start with the Minamata example as I was planning to ask you, and then as our colleague also asked. So looking back at the Minamata example, how could we have applied these material flows? Uh, does anyone want to suggest where it could have been applied? There are several ways there are several systems to what this could be applied, and several outcomes we could have from that. So could someone suggest one problem that we would like to look at in the Minamata example? So what would be our question to start the analysis? If anyone could cite at least one, I can cite the other ones that I'm thinking about. Where the mercury is going, right? So you're talking about from the industrial process to the environment, right? We could look at environmental discharges and nothing else. Yes, we could look. The focus would be the outcomes to the environment from the industrial processes. Agree. I would also suggest two other analyses which could be interesting. One would be a material flow analysis for the environment. So I think the problem was linked to emissions in the bay. Although I guess atmospheric emissions would be a problem too, but they don't talk much about it. But yeah, let's say, so we could do a balance for the bay. So looking at, if we could clearly characterize the industrial discharges, as our friend said, then we could shift our balance to look at where the mercury goes once it comes into the water. can map, how much is coming in, how much is being emitted to the atmosphere, how much is being accumulated in the food stocks and then being extracted to the anthroposphere via capturing fish and seafood from the bay and also water. So that would be another way of doing it. We can also do the analysis for the industrial process, looking at where the mercury is coming from to that industrial process, and then looking at where it goes in the industrial process and then how it's being discharged. And the reason to do that would be, first, if we are not clear about how much is being discharged. So if we don't have measurements of the discharges to the environment, we could have applied that to figure out how much possibly is being discharged in the environment by closing the balance. We also could use that to understand where inside that chemical plant the mercury is going, to then look at containment strategies, where we could put a treatment plant or where we could put a secondary containment to avoid the discharge to the environment. So that's another application for that. How would we have done that? Yes, so we defined our problem, we would define the boundaries. So suppose we decide to do the analysis so suppose we detect that there's mercury coming to the environment, but we cannot quantify the flows. So one of the main objectives of our analysis would be to figure out how much is being discharged in the environment by doing a balance for the chemical plant. So now we define our problem, right? We want to understand how much is being discharged in the environment, and hopefully we understand how it's flowing internally in the plant to help us figure out containment strategies. Then we would define the system boundaries, so possibly would be the actual physical boundaries of the chemical plant. We possibly will be looking at a 1-year time frame to understand, all the cycles that the plant goes through. After that, we would have to map the flows within the plant. So possibly you understand that the industrial process will be straightforward because, of course, the people operating the plant would have information about which processes they are doing there and how much they transport here and there, because that's operational information important for them to keep the plant going. That information will be in terms of goods or at least mixed substances, right? So they have, and we will have the imports very well characterized too, because the imports will be the things that they buy. So they know exactly how much they buy. That's a good point. So they know exactly how much they buy. So they will know, we bought this much of precursors of the acetaldehyde. That's what they produce in the plant. And this much of this material containing the mercury. And then this go to this and that process. So we would have a clear map of those flows. If the chemical compositions are not clear, we might have to do some actual sampling and analysis to figure out the content of mercury in each of those inputs and each of those internal flows. And with that, we would be able to look at the flows of mercury and the changes in stock. And then we would be quite safe to conclude that whatever we need to balance that inflows and changes in stock would be the outflows to the environment. Breaking down the outflow to the environment could be more challenging because it's not clear there if the discharges were in a wastewater. Because if the discharges they are pipeline, it's easier to analyze. If they come from a stack as gaseous emissions, or if they come as solid waste, or if they come as a wastewater, it's kind of easy to analyze because we can easily measure flow rate, and we can easily measure sample the concentration in that and do a simple calculation of mass flow. If the emissions are diffused, much more complicated. So if they come from runoff, if they come from they go to the soil and they infiltrate in the groundwater, or if they go to the soil and then because it's mercury evaporates to the atmosphere, then we'll have a high level of uncertainty in that. So it may have just the overall, but not exactly how much goes in each way, or we have a high uncertainty of how much goes in each way. Does that illustrate well how that would be done? How that would be done? Any questions about the process? All good? Cool. Thanks for the contribution, people. It's always very, very useful, very nice to hear your perspectives. So we quickly go here through some examples of application. We will not detail them, just to give you an idea of how that can be used. So one would be to understand the phosphorus cycle in the environment. So here is just like a schematics of how the cycle works. And then we might be interested in, for this phosphorus problem, we're interested in different aspects. One of them is demand on the environment, because phosphorus normally is mined and our phosphorus reserves are depleting quite quickly, and this is one of the most impeding environmental problems and economic problems we may have in the short-term future. Depletion of phosphorus reserves. If we lack phosphorus for our fertilizers, we have massive trouble with agricultural production. But we also might be interested in emissions of phosphorus to the environment. Once it is used in natural or planted environments, how much leaches to the groundwater and how much goes to the water bodies is important, because phosphorus in the wrong place may cause algal blooms, may cause eutrophication. So we could use a material flow analysis to understand both of these aspects. And we can also do it for a given economy, again, to understand these aspects in a larger scale. So this is a balance of phosphorus for UK. And what you see is that there is a lot of accumulation in here. And possibly most of this accumulation will be in the soils and the plants and in the biomass produced here, but also it may be linked to eutrophication, because where is this phosphorus being accumulated? And then you can break it down in much more detail. So this is like a very typical type of diagram that comes from material flow analysis, and here you have a breaking down in different activities such as grazing and fertilizer manufacture, and then you have this fertilizer use as up, and you have it being exported as well. So you can break it down quite nicely. At first, when you look at this, sounds very complicated, but if you try to map individual flows, then it's cool. Or if you want to see where is the whole waste comes from, you can look at where the waste comes from several processes here, including the food supply. And then you can look at, then that can help you plan actions to, let's say, minimize waste, or to increase recycling here as manure or as compost back to this, which then will reduce the demand from natural stocks. Here we have a similar analysis where they do this for the Australian food system. And then they use that to then make conclusions about phosphorus security, which, as I said, it is a big deal. And this is, again, illustrated in a different way, but very clear, very similar also with similar to the examples we saw, the generic examples we saw in class. And this is like, here's a detailed balance. This is like a black box balance for the whole of Australian agriculture. So this is now doing the balance for sector, aggregating all the processes in that sector. Here again, we see quite big accumulation in it. And this is where the phosphorus grow in the wastewater process, and why we're interested with that. Why would be interested in looking phosphorus balance in the wastewater? Does anyone have suggestions why would look at that? Well, one of the reasons is because we wanna increase the recycling of the phosphorus. So of this total phosphorus coming in the wastewater, if we could ideally make it circular and then be able to extract it back either as inbuilt in the biosolids, extracted via other processes and put it back in industrial process or other like industrial process or agriculture or anything where phosphorus is beneficial, it would help us then deplete less our natural reserves and also have to, if we're importing it, import less from other countries. Second is because we are worried about this, the emissions of phosphorus to water, especially. And why is that? Because that is a problem in terms of eutrophication, as I said before. Then this is another example on how this is being used to extend the flows of nutrients through Great Barrier Reef. And the problem is if we have a lot of nutrients, we imbalance the diversity of species here and we have excessive overgrowth and then we change the diversity of that environment. This is just some examples of how this was used to quantify the anthropogenic load and then to also look at load reduction over time to see how well certain strategies to minimize the output, how these strategies are performing. Then this is another example of looking at aluminium in packaging. So here they are looking for a given substance and in a given industrial process or a given economical sector, which is packaging. And then they're looking at that to help improve circularity. So if they were able to map the flows and map the losses, and then they could identify where are the opportunities to implement actions which will improve the recycling and reutilization of that aluminium back to the same economy without having to first, well, of course, avoid imports of that from nature and from other countries, and also to avoid wastes. And here they did it as a product basis. So here's an example of a work from my colleague, Dr. Ruth Fisher, who used to be a lecturer of this course in the past too. And she applied that concept to understand the sulfur flows in the wastewater treatment plants. And why she wanted to look at that? Well, because sulfur is useful if it goes to the biologists and it is applied to land. So it's like a micronutrient for plants and for other organisms. But it's also a problem because it can be related to definitely odorous substances, it smells bad, and some toxic emissions potentially. So she tried to understand that balance of sulfur in the wastewater treatment process. Again, to look at uh, where potential emissions will come from and where are the opportunities for recycling. This is just the wastewater treatment process, and this is breaking down the biosolids treatment process. So in practice, just to conclude our class, it will depend on data availability. So how detailed you can do this balance and how confident you are in the outcome balance will depend on data availability. And this data availability, as I said, for industrial processes, mapping the processes is quite easy. For natural processes, not always. So not necessarily we are confident that we know all the natural flows and all the natural pathways that can exist. But then the reliability of the quantitative data that we use to do this analysis is also a point. So as I said, for certain processes, we still don't have clear ways of measuring it systematically. And it's cool because then if we have this uncertainty, tools such as STAN that I've mentioned before, they can be used. They can have inbuilt in them this uncertainty analysis and error propagation at least to have an idea of how confident we are in the outcomes. And they can help us identify missing flows of poor quality data, as we said. So if the balances don't fit well, it's either because we missed some aspect or the data is not good enough. Yes, in principle, we should be able to at least predict that those flows could be there, and it's desirable that we have ways of quantifying them, or at least have an idea of their magnitude to be able to properly close the balance. Our colleague is talking about flows which are unintended, so it's not always well monitored. So these are where you can apply. So we had several examples there. I will not repeat all of them. And it will depend on which flows you're looking at and which is the purpose of what you're doing. We can use it for resources management. That's super interesting. And one of the interesting ones is forecast scarcity of resources and link resource management to waste management, because then we will map how what we are taking from nature is being converted in outputs to the nature again. And then we can look more clearly in waste management to look at which is the elemental composition of these wastes and define opportunities for recycling and how we can better manage that, and also look at sewage sludge management and even the sewage management itself. And there is on Moodle an example of that which exemplify or discusses this material flow analysis as a tool to help make decisions on waste management systems. But which are the limitations of this method? What we cannot achieve by doing a material flow analysis? So, although for certain substances the impacts are pretty straightforward, so if we say, well, people are having trouble with mercury, they're having disease caused by mercury, by looking at how much mercury we put in the environment, we are still not quantifying that impact, but we can directly make that link. For other substances, the impact is not as direct. So here we're looking at balance of substances and materials and goods. The environmental impacts they cause not necessarily is straightforward. Back to that example of emissions of odors from a wastewater treatment plant, we can quantify the emission, but the impact of that emission will depend on several factors, like how far the plant is from the community, the wind directions, the capacity of the atmosphere to dilute and disperse that pollutant. So converting the substances into impacts will require a further analysis, which is out of the scope of the material flow analysis. We cannot predict changes in the stock directly. And we will see, in fact, in our workshop today, we will try to make a prediction like that, but to do that, we have to predict the flows. And then this, again, doesn't come directly from the material flow analysis, but it comes from an independent assessment. So if you say, well, we will be living here producing this, we have a plant here, which will operate for 30 years with this production capacity, and if you think that production capacity will remain the same, you can pretty much say how much we will demand of inputs and how much of outputs you will have. So in a case like that, you can predict flows and predict changes in stock. But there are cases where you cannot make that prediction. And again, the bigger your system becomes, the harder it will be to make such predictions. And we also cannot show consumption of natural resources, such as we do with even with as the hidden flows in economy-wide material accounting, or as environment ecological footprint. We do not look at if we're doing the analysis for one substance, we don't look at all the other substances which are also impacted. And also we're not saying anything about energy. So we're not doing the energy balance of process, although the same framework could be used for a energy balance as well, but we'll not call it material flow analysis. Cool. So this is just some final concluding points. It can help us to understand the metabolism of the anthroposphere and of the natural systems. it can help us with anticipatory environmental management when we can look as a predictive ability in terms of if we determine certain significant flows from or to the environment, we can then predict, well, this will become a problem in the future. Let's act on reducing this now. And then we can also use that to assess current environmental problems, as we've seen so many examples with the barrier reef, with the Minamata project, with problem we said, and so many other examples that we talked about. Great. Any questions or any final comments before we conclude our lecture? Just a final reminder, we have assignment submission end of this week. I've been receiving questions on the email, but if those questions are of general interest, please post them on the Moodle forum. So normally when I receive those questions, I ask the person to post there, and I quickly go and reply it as soon as I can. All right, I'll keep monitoring Moodle forum there. This is still the best way to ask questions besides asking questions now during the lecture or during the workshop. But yeah, keep in mind the submission date deadline. If you don't have any questions about the lecture, so I will give you some break before workshop starts, all right? For those who are in my workshop, see you soon. For the other ones, see you guys next week. Thanks. Thank you. I will stop our sharing and I will stop recording.